Hi. So in this video, I'm going to talk about the example of a divide and conquer algorithm for fast multiplication. This is in the course notes, but it's a little dry, so I thought making a video would spice things up a bit. So here's the situation. We have x and y, two n-digit numbers. And we're going to look at the running time of different operations on x and y. And what do I mean by runtime? The runtime is going to be measured in the number of one-digit operations. This might seem a little arbitrary, especially given that up to this point in this course, we've been assuming that addition and multiplication of numbers takes constant time, no matter what the numbers actually are. But of course, in practice, if you're dealing with very large numbers, say hundreds of digits long numbers that don't fit into a single machine word, and somehow you'd expect the size of the numbers to determine how long it takes to add them or multiply them. So as a warm-up, let's consider addition. If we have these two numbers x and y, and we want to add them together, what's the natural thing to do? 2 plus 5 is 7, 1 plus 1 is 2, and then for each pair of numbers, we add them together. And of course, we have to keep track of carries, but that doesn't take very much effort. If we're looking at the number of one-digit operations, well, this is just the number of columns, which is the number of digits. So this requires big O of n one-digit operations. What about multiplication? Well, here things get a bit more complicated, because now we have to multiply, say, 5 times 2, then 5 times 1, carrying the 1, and then 5 times 3. And we need to multiply this 5 with every single digit in x. And then what do we do? Well, we have to take this 1 and multiply it with every single digit in x. And then we have to keep on doing this until we end up with 9 times 3 somewhere at the very bottom down here, and then add up the columns. This is the standard multiplication algorithm that we all learned in grade 2. If we look at just the multiplications, it's not hard to convince yourself that in fact there's n squared multiplications. Because for every digit in y, we have to multiply it with a digit because for every digit in y, we have to multiply it with every digit in x. And what about the additions at the end? If you look at the numbers that you've actually written down everywhere, you can see that every row has n numbers, and when you do the addition going down, there's n rows. So again, there's going to be n squared additions for a total of big O of n squared one-digit ops. So the divide and conquer algorithm that I'm going to show you next is going to beat n squared. So what's the idea? Here's your x, n digits long. Here's your y, n digits long. We're going to divide and conquer. So split up x and y into two parts so that these components, x1, x2, y1, and y2, each have a length of n over 2. And now let's use a bit of math. We can write x as x1 times 10 to the n over 2 plus x2. And similarly, we can write a similar expression for y. So to multiply x and y, it's enough to multiply these two expressions. And what was the point of doing that? Well, we've managed to reduce the problem of multiplying 2n by, we've managed to reduce the problem, and what was the point of doing that? We've managed to reduce the problem of multiplying two n-digit numbers into a bunch of multiplications of n over 2 digit numbers. But wait, David, you're thinking, what about the multiplication by 10 to the n and 10 to the n over 2? Well, I'll get around that by saying that sort of multiplication can be done in constant time because all it involves is adding a bunch of zeros at the end. If we were working on a computer, we probably wouldn't be working base 10, but instead base 2. But the same logic would apply. We could implement multiplications by powers of 2 as just shifting the bits over, which can be done in constant time. So I'm going to ignore those multiplications. It's pretty easy to see how you can get a recursive algorithm for multiplying numbers using this formula. So I'm not going to write it out for you here, although if you're a little stuck at this point, pause the video and find this in the course notes. Let's see what recurrence we get from this algorithm. If n is the number of digits in x and y, then what is t of n equal to? We do 1, 2, 3, 4 recursive multiplications where each input, x1, y1, or x1, y2, they have size n over 2. And then what's the non-recursive cost? Well, I already said that multiplying by powers of 10 is constant time, but keep in mind that we still have additions as well. So in fact, the non-recursive cost is linear, because as you remember from a few minutes ago, we can add n-digit numbers in linear time. Let's analyze this using the master theorem. A is equal to 4, b is equal to 2, k is equal to 1, log base 2 of 4 is equal to 2, and since 2 is bigger than 1, the running time of this is n squared. Oh dear. Remember that the elementary school algorithm we got was an n squared algorithm? So therefore, this divide and conquer approach didn't actually help us at all. We might as well have just taken these two numbers and given them to some grade 2 students to multiply for us. But as was the case with closest pairs in class, we can use a mathematical idea to simplify our calculations. So let me remind you, our previous algorithm needed to compute the following 3 coefficients. And the naive way to do this was to compute each product separately, resulting in 4 products. The big mathematical idea is that this doesn't really require 2 multiplications to produce. Why? Because of the following product. So that was just some simple algebra. But what it shows is that if we want this term, we can get it by first computing this, and then subtracting the other 2 products we had to compute anyways. We only need 3 recursive multiplications, not 4. Now our recurrence becomes t of n is equal to 3 t of n over 2 plus dn. Now we have a is equal to 3, b is equal to 2, k is equal to 1. And so the algorithm runs in time n to the log base 2 of 3, which is approximately n to the power of 1.585 something. Again, this problem isn't as flashy as the closest pairs problem we saw in class, but it is a really neat example of divide and conquer beating some grade 2 students. Thanks for watching and have a great day.